History is filled with silent monuments whose secrets seemed lost forever. We are about to unlock 20 of them, not with guesswork, but with hard science. You will discover the exact methods ancient builders used to achieve the impossible, from moving pyramid stones to forging unbreakable concrete. How did Romans create harbors that heal themselves in seawater? What simple trick let Egyptians slide massive blocks across the desert? This journey through proven ancient construction techniques reveals a forgotten textbook of human ingenuity, written in stone, wood, and earth. It shows that our ancestors were master engineers, solving problems with a brilliance we are only now confirming. Which ancient innovation do you believe was the most visionary? The silent stones of history hold more than just weight, they hold instructions. To read them, we need a new kind of language, one built not on words but on action. This is the core of experimental archaeology, a discipline that treats the past like a grand, unsolved equation. It begins with a simple, powerful question: how was this done? From there, it moves beyond theory into the tangible world of physical proof. Researchers become detectives and craftspeople, meticulously recreating the exact conditions an ancient builder would have faced. They source the same local clay, shape tools from the same type of flint or bronze, and follow the subtle clues left behind, the unique wear patterns on a chisel, the specific angle of a cut in a timber. The goal is not to put on a show, but to run a controlled experiment. If a proposed method for moving a multi-ton block actually works with the period's available technology and leaves the same physical evidence found on the original artifact, then a hypothesis becomes a demonstrated fact. It transforms a mysterious monument from a static object into a dynamic story, a recorded moment of human ingenuity, effort, and triumph. This rigorous, hands-on science is the very foundation of our journey. Every technique we explore has been put to this test, moving from the realm of interesting guess into the ledger of historical reality. This process of proof is a dialogue with the past, one that demands answers that work in the real world. So what exactly separates a plausible theory from a proven technique? The standard is deliberately high and beautifully simple. For a method to be considered proven, it must pass a series of rigorous physical tests. First, it must be functional. A team must actually complete the task, whether that is raising a multi-ton stone into place or creating a watertight joint from start to finish. Second, it must be efficient enough to be plausible within the known time frames and social structures of the culture. A method that requires 10,000 people for a single block is not a solution. It is a different kind of mystery. Third, and most crucially, every element must be historically attested. This means using only materials, tools, and sources of power, like human labor or domesticated animals, that were definitively available at that time and place. No hidden steel cables, no modern machinery, no secret chemical compounds. The final, and perhaps most elegant, test is the evidence the experiment leaves behind. The wear on a rope, the specific scratch pattern from a wooden sled, the microscopic residue in a mortar mix, these physical signatures must match, like a fingerprint, those found on the actual ancient structures. This criterion turns speculation into science. Every failed experiment, every idea that collapses under the weight of its own impracticality, is not a setback but a step forward. It clears the path, ruling out the impossible and bringing the true methods of the ancients into sharper, more brilliant focus. It ensures that what we are about to explore is not imaginative fiction, but recovered knowledge, the demonstrable genius of our ancestors waiting to be understood once more. The mystery of the pyramids begins not with their towering height, but with a simple, staggering question of logistics. How did thousands of multi-ton limestone blocks travel from distant quarries to the construction site? For decades, the sheer physical improbability fueled speculation of impossible technologies. The answer, however, was hiding in plain sight within a single ancient image. A tomb painting from around 1880 BC shows a colossal statue being pulled on a wooden sledge. What makes the scene remarkable is the detail often overlooked: a figure standing at the front of the sledge, carefully pouring a liquid onto the sand directly in its path. For generations, this was interpreted as a ceremonial act, perhaps a libation. Experimental archaeologists saw it as a direct instruction manual. A team from the University of Amsterdam decided to test the practical effect. They built a replica sledge, loaded it with weight, and tried pulling it across dry desert sand. The resistance was immense, with granules piling up into a formidable ridge before the runners, creating a literal sand wall that had to be constantly cleared. Then they dampened the sand just ahead of the sledge. The result was transformative. The required pulling force was halved. The damp sand did not stick to the sledge. It did not form a ridge. The secret lies in the physics of water. When sand is just damp enough, the water forms tiny bridges between the individual grains, binding them together. This creates a firm, almost pavement-like surface for the wooden runners to glide across, drastically reducing friction. This proven technique reframes the entire endeavor. It was not a brutal struggle against nature, but a masterful collaboration with it. The desert itself became a prepared highway. A large crew, using ropes and this simple application of water, could move blocks with a coordinated efficiency that makes the monumental task suddenly, brilliantly plausible. It reveals a profound intelligence, a willingness to observe a natural property of their own environment and harness it on a breathtaking scale. The first great lesson from experimental archaeology is this: ancient genius often lies not in complex machinery, but in the elegant application of a simple, observed truth. While the Egyptians mastered the desert, Roman engineers performed an even greater feat. They conquered the sea. Walk along the crumbling edges of a modern concrete pier, and you see the inevitable damage from salt and waves. Now look at the ancient harbor of Portus, which served Rome for centuries. Its concrete structures have not merely survived 2,000 years of Mediterranean storms, they have thrived. For a long time, this was considered a happy accident, a lucky combination of materials. Modern experiments have revealed a stunning truth. The Romans did not just make strong concrete. They engineered a living material designed to grow stronger in the very element that destroys our own. The key was their specific recipe, a mix of slaked lime, volcanic ash from the region of Pozzuoli, and chunks of rock. When modern researchers meticulously recreated this mix and submerged samples in seawater tanks, they witnessed a slow miracle. Instead of corroding, the Roman concrete underwent a unique chemical conversation with the salt water. Seawater seeping into the microscopic pores triggered a long-term reaction, forming rare, plate-like minerals such as aluminous tobamorite and philipsite. Think of these not as signs of decay, but as a built-in repair system. These crystals gradually grow, intertwining to fill any tiny cracks that form, effectively healing the concrete from the inside out. This proven process, called seawater catalysis, flips our entire understanding on its head. The Romans did not see seawater as an enemy to be kept out. They designed a material that welcomed it, using the sea's own chemistry to forge an unbreakable bond. Their harbors were not static monuments, but dynamic, resilient partners with the ocean. This level of material science was not matched again for over a millennium, a testament to a civilization that thought in terms of centuries, not just decades, building legacies meant to endure the relentless test of time. The Romans built with a living material, but the Inca builders of the Andes performed a different kind of alchemy. They made stone flow like clay. The walls of Machu Picchu stand as the ultimate expression of this art, massive granite blocks joined without a trace of mortar, fitting together with a precision that seems to defy the very nature of rock. For centuries, this appeared to be a mystery of pure, patient craftsmanship, an endless cycle of grinding one stone against another. Experimental archaeology, however, revealed a more dynamic and intelligent process, one that began not with shaping, but with a controlled act of creation. The technique likely started at the quarry face. Builders would carefully carve a line of shallow holes along a granite outcrop. Into these holes, they inserted dry wooden wedges. The next step was the key. They soaked the wedges with water. As the wood absorbed the moisture, it expanded with a slow, relentless force, generating enough pressure to cleanly split the stone along a perfectly straight, predetermined plane. This was not crude breaking, it was precise geological surgery. It gave them a manageable block straight from the living mountain. The shaping came next, proven by the distinctive textures left on the stones themselves. Using hammerstones of even harder rock, workers would pound the surfaces, gradually knocking off small chips and dust. This pounding process, tested and shown to replicate the exact dimpled surfaces found on Inca ruins, allowed for incredibly fine adjustments. It was a conversation between the worker and the stone, a tactile feedback loop where each strike could be felt and judged. The final, breathtaking fit was achieved by repeatedly fitting one block against its neighbor, marking high spots, and patiently pounding them down until the two stones locked together, often so tightly that not even a blade could slip between them. This proven method reveals a philosophy as much as a technique. It was not about conquering the mountain, but about understanding it, using its own inherent properties, the expansion of wood, the fracture lines of granite, as partners in creation. The Inca mason did not merely cut stone, he persuaded it, guiding it from a raw piece of the earth into a perfect, interlocking piece of a lasting whole. The transition from stone to wood might seem like a step toward simplicity, but it presented its own monumental challenge. Imagine the task facing Neolithic communities across northern Europe, standing before a cleared circle of earth, with a series of massive, freshly felled oak trunks lying beside deep, waiting holes. The goal was not merely to plant trees, but to raise a sacred architecture, to transform a forest strength into a permanent enclosure for ceremony and gathering. For sites like Woodhenge, the precursor to Stonehenge, the question was one of pure physics. How do you lift a multi-ton wooden pillar and drop its base perfectly into a narrow, deep socket without it shattering or toppling? Experimental archaeology at places like Buttresses Ancient Farm has proven the answer lay not in magic, but in a symphony of coordinated human effort, guided by simple machines. The process began with preparation. The base of the giant post was tapered to a point, and the post hole itself was dug with one side sloped into a ramp. The trunk was then rolled until its base rested at the ramp's bottom, its length pointing up the incline. Here, the simple genius of the A-frame lever came into play. Two large wooden A-frames were erected on either side of the post hole. Ropes were lashed around the upper portion of the oak trunk, run over the apex of the A-frames, and gathered by a large crew. On a coordinated chant, the crew would pull, using the A-frames as giant pivots to convert their horizontal pull into a vertical lift. It was a rhythmic dance of strain and incremental victory. As the post rose, other workers used long poles as secondary levers to guide it, while still others stood ready to jam temporary wooden rails and packing stones into the hole to stabilize the giant timber as it neared vertical. The final heart-stopping moment was the controlled drop as the base slid off the ramp and settled into the precise center of the hole, immediately packed tight with stone and earth. This proven technique leaves a clear archaeological signature, distinct soil compression patterns from the ropes and guide rails, and specific tool marks around the post hole's edge, all of which match excavations perfectly. It reveals a society capable of breathtaking organization, where the strength of many, directed by a shared rhythm and a clear plan, could achieve what no individual ever could. They did not just build with wood, they conducted it, raising a forest into a temple through the fundamental power of united purpose. The same principle of flexible strength guided master shipwrights in a very different and far colder theater of engineering. To the Norse, the sea was not a barrier but a highway, and their vehicle was a masterpiece of adaptive design, the Viking Longship. For decades, these vessels were icons of history, their sleek forms preserved in burial mounds, but their true capabilities remained a subject of debate. Could a wooden ship built over 1,000 years ago really withstand the violent, unpredictable fury of the North Atlantic? The answer did not come from a textbook, but from the heave of a deck and the sting of salt spray on a modern crew's faces. Experimental archaeology took to the waves with full-scale reconstructions like the Sea Stallion from Glendalough, a ship built using only attested tools and methods, then sailed on a 4,000-mile journey from Denmark to Ireland and back. This was not a simulation, it was a brutal, real-world test, and it proved the Viking technique was not just functional, but phenomenally so. The core of their genius was the clinker-built hull. Instead of laying a frame first and attaching planks to it, as in later shipbuilding, Norse craftsmen started with the shell. They took long, radially split oak planks, a method proven by experiment to follow the wood's natural grain for maximum strength and flexibility. These planks, called strakes, were carefully overlapped and riveted together with thousands of hand-forged iron nails. The result was a hull that behaved like a living creature. When a massive wave struck, the entire structure could flex and twist, absorbing the energy rather than resisting it until it shattered. This was a ship designed to dance with the ocean, not to stand rigid against it. The experiments also confirmed the vital role of the caulking, known as wadmal. Workers would drive strands of woolen yarn, soaked in sticky pine tar, into the seams between the overlapping planks. As the ship was launched, the wool would swell with water, creating a perfect, self-tightening seal that kept the vessel dry even in the roughest seas. Every detail, from the subtle curve of the keel to the precise placement of the single, massive square sail, was refined through generations of hard-won experience, a knowledge now validated by modern voyages. These ships were not merely transportation, they were the very engine of an age, enabling exploration, trade, and cultural connection across vast distances. They stand as a proven testament to a philosophy of building in harmony with the forces of nature, creating not just a tool, but a partner for conquering the unknown. Yet the most enduring architecture often begins with the humblest of materials. In the sun-scorched plains between the Tigris and Euphrates rivers, the great ziggurats and sprawling city walls of Mesopotamia were not carved from stone or timber. They were born from the earth itself, a testament to a profound understanding of a simple substance, mud. For generations, scholars noted the countless fragments of straw visible in ancient mud bricks, but assumed it was merely cheap filler, a way to stretch scarce clay. Experimental archaeology transformed this assumption into a proven engineering principle. Teams began by gathering local clay, just as ancient builders did, and forming it into bricks. One batch was pure clay, another was carefully mixed with a precise proportion of chopped straw, a material readily available from the region's grain harvests. The difference, once the bricks dried, was not subtle, it was fundamental. The pure clay bricks shrank unevenly as they lost moisture, forming deep, structural cracks that ran through their core. They were brittle, crumbling easily under pressure. The straw-tempered bricks, however, dried slowly and evenly. The organic fibers acted as a microscopic reinforcement network, a three-dimensional web within the clay. As the clay contracted, the straw distributed the internal stresses, preventing large cracks from forming. It was a perfect marriage of material science and available resources. When subjected to simulated weathering tests, the tempered bricks proved vastly more durable, resisting the crumbling that would doom a wall or a foundation. This proven technique reveals a deep, accumulated wisdom. It was not just about making bricks, it was about transforming a fragile, temporary material into a permanent one. The straw, far from being mere filler, was the essential ingredient that allowed mud to defy the desert sun and the rare but torrential rains for centuries. It turned the very ground beneath their feet into a reliable, monumental building block, enabling the rise of the world's first great cities from the dust. The sheer weight of stone presents a universal challenge, one that found a brilliant answer in the clear logic of Greek and Roman engineers. High on the Acropolis, the marble blocks of the Parthenon rest in perfect, elevated harmony, a sight that begs the practical question of how they ever got there. Ancient texts such as those by the architect Vitruvius provided the clues describing machines called cranes. Yet for centuries, these descriptions remained abstract sketches on a scroll, their true power untested. It took the hands of experimental archaeologists sawing timber and twisting hemp rope to transform those sketches into functioning reality and prove their astonishing capability. The fundamental machine was the trispastos, a wooden derrick powered by a simple winch and a single pulley block. By reconstructing it with period-accurate materials, researchers demonstrated its elegant efficiency. A small crew, perhaps 5 or 6 individuals walking in a circle to turn the winch, could lift a multi-ton block smoothly and controllably. The secret was not in raw strength, but in the redirecting force of the pulley, which changed the direction of the applied effort and provided a basic mechanical advantage. But the Romans, masters of scaling innovation, took this principle further with the polyspaston. This machine incorporated a system of multiple pulleys working together in what we now call a compound block. The reconstruction and testing of this device yielded a staggering result. The compounding effect of the pulleys created such a dramatic mechanical advantage that a crew of similar size could lift several tons with a relative ease that seems to defy belief. The proven operation of these cranes reshapes our understanding of ancient construction sites. It dispels the enduring myth of endless, anonymous slave labor straining against impossible weights. Instead, it reveals a sophisticated worksite where intellect was the primary tool. The crane was a force multiplier, a machine that allowed skilled workers to apply precise, coordinated effort. It turned the act of lifting from a brutal struggle into a calculated operation of physics. This was a society that did not just build grandly, it thought grandly, using the clear principles of mechanics to elevate not only stone, but the very potential of human achievement. The quiet turning of a wooden winch, guided by geometry, could raise a civilization's most enduring symbols toward the sky. The crane harnessed physics to lift stone, but a different kind of genius lies in letting wood move. In the forests of Japan, temple builders achieved a timeless stability not by fighting nature's forces, but by welcoming them. The soaring pagodas and serene halls, assembled without a single nail, represent a pinnacle of carpentry where every joint is a conversation. For centuries, the secret of their survival through relentless earthquakes was a beautiful mystery locked within the wood itself. Experimental builders have become translators, meticulously recreating joints with names like shigachi and kanawatsugi. These are not simple connections, they are intricate, three-dimensional puzzles carved from single pieces of timber. The process is one of profound patience and precision, where a master carpenter reads the grain of the wood like a map, shaping tenons and mortises that fit together with a satisfying, airtight click. But the true test came when these reconstructed frames were placed on modern shake tables, machines that simulate the violent, chaotic energy of an earthquake. The results were revelatory. As the simulated ground shook, the complex joinery did not resist rigidly, it danced, Each joint flexed, twisted, and absorbed the seismic energy, dissipating it through the entire lattice of the structure. Some joints are even designed with a brilliant locking mechanism, where increasing force causes the interlocking pieces to tighten their grip, becoming more secure as the tremor intensifies. This proven dynamic behavior explains a historical miracle: why pagodas that have stood for 5, 7, even 10 centuries have weathered countless tremors that flattened modern, rigid buildings around them. It is a technique that proves an advanced, almost intuitive understanding of material and force. The builders knew that wood, when respected and connected correctly, possesses a living resilience. They achieved legendary durability not through brute reinforcement, but through intelligent design that partners with chaos, allowing the structure to breathe, flex, and ultimately endure. It is architecture as a living system, a lesson in humility and brilliance carved in cedar and cypress. Stone can be taught to fly. In the heart of medieval Europe, master masons performed this very miracle, transforming the dense, earth-bound nature of their material into structures of breathtaking lightness and grace. The great Gothic cathedrals, with their skeletal stone frames and walls of luminous stained glass, stand as a direct challenge to logic. How could such delicate-looking stone cages support the immense weight of a roof and withstand the relentless push of the wind? The secret was externalized, written in the elegant stone arcs that leap from the cathedral's sides like the ribs of a great stone beast. These are the flying buttresses, and for centuries their precise function was a subject of architectural theory. Experimental archaeology, using both physical models and advanced digital simulation, has now proven their role with concrete, measurable certainty. Researchers built scaled-down versions of Gothic vaults and their external supports, instrumenting them with sensors to measure the exact flow of forces through the stone. The results revealed a brilliant system of load distribution. The stone roof or vault does not simply press down, it pushes outward with tremendous lateral thrust. Without intervention, this force would cause the walls to bulge and collapse. The flying buttress intercepts this outward thrust at a high point on the wall. Acting as a lever, it catches this push and redirects it down along its own sloping arch, channeling the energy safely into a massive external pier and ultimately deep into the ground. This proven action is what liberated the wall from its load-bearing duty. The thick, fortress-like walls of Romanesque churches could now be hollowed out, replaced by vast windows that filled the interior with a heavenly colored light. The experiment confirms that every curve of those stone arcs was a calculated response to physics, a structural innovation that turned solid masonry into a dynamic framework. It was not mere decoration, but the visible logic of a new architectural language, one that allowed faith and light to be built from stone and sky. The softest metal can cut the hardest stone. This apparent paradox lies at the heart of another Egyptian mystery, found not in towering monuments, but in delicate, polished vessels. Archaeologists have long marveled at exquisitely carved vases made of diorite and granite, stones so hard they can scratch modern steel. The most telling clue was the drill hole often found at their center, a hole with a very specific signature, a perfect spiraling groove etched into the stone. For years, this seemed impossible with the known technology of the time, copper tools. Copper is malleable, far softer than the granite it was supposed to have cut. The solution was not in a harder metal, but in a clever partnership between materials. Experimental archaeologists set up a simple apparatus, a hollow copper tube fixed to a bow drill. They prepared a simple slurry of water and ordinary quartz sand, which is significantly harder than granite. As the copper tube was rotated under pressure against the stone surface, something remarkable happened. The soft copper did not cut the stone. Instead, it acted as a carrier. The abrasive quartz particles in the slurry became embedded in the copper's leading edge, turning the entire tube into a grinding saw. With patient, sustained rotation, this embedded abrasive slowly, relentlessly wore away the stone, grain by microscopic grain. The hollow tube core allowed the abrasive slurry to continuously feed into the cutting face, while the removed stone dust, called swarf, was carried up inside the tube. This proven process perfectly explains the helical grooves in the ancient holes. They are the literal fossilized record of each individual quartz particle's path as it was dragged in a continuous, grinding spiral. It reveals a profound conceptual leap. The Egyptians understood that the tool itself did not need to be hard, it needed to be a vehicle for hardness. They mastered the principle of relative hardness, using a locally abundant, mundane material, desert sand, to achieve a level of precision that seems almost modern. This was craftsmanship built not on force, but on relentless, patient friction, a quiet testament to the power of understanding the hidden relationships between the simplest of things. The genius of a structure often lies in how it listens to the landscape. Across the vast, wind-swept plains of North America, where timber was scarce and the seasons swung between bitter cold and searing heat, native communities developed an architectural solution that was not imposed upon the earth but drawn from it. The Earth Lodge, a semi-subterranean dome that seems to rise from the ground itself, represents a profound dialogue between human need and natural resource. For generations, these structures were known only from archaeological remains, circles of post holes and depressions in the soil. But to truly understand their sophistication, researchers had to build them again, following the whispers of tradition and the logic of the materials at hand. The process begins with the most vital element, the bones of the structure. Experimental reconstructions, led by tribal knowledge keepers and archaeologists working in partnership, have proven the critical choice of material, young saplings of willow or cottonwood. These trees were not cut and rigidly joined, they were carefully selected for their youthful flexibility. Workers would bend the green saplings into graceful, living arches, setting their ends into a circular trench dug into the earth. These arches were then lashed together at the top with strips of pliable bark or sinew, creating a strong, interlocking lattice, a dome of wood that was resilient because it was designed to give, not just to hold. Over this sturdy framework, layers of insulation were added, thick bundles of grass, then sod, and finally a blanket of packed earth. The completed lodge was not just a building, it was an extension of the prairie itself. The experimental projects put this design to the ultimate test of lived experience. During winter, temperature sensors placed inside the reconstructed lodges recorded a remarkable stability, the thick earth shell trapping warmth from a central hearth. In summer, the same mass of earth kept the interior cool and shaded. The covering proved its worth against the relentless plains wind, which flowed over the dome with little grip and even offered significant protection from the threat of prairie fires. These experiments confirmed more than just comfort, they demonstrated a complete system of sustainable engineering. Every component was local, renewable, and required no specialized tools beyond human skill and knowledge. The bent sapling frame used minimal wood for maximum volume and strength, a lesson in material efficiency. The Earth Lodge stands as a proven testament to an architecture of harmony, where shelter was created not by conquering the environment, but by understanding its rhythms and borrowing its strength, crafting a home that was truly of the land. The same principles of moving air and heat that warmed ancient homes also shaped the very land around them. While the Romans mastered indoor comfort, another civilization on the opposite side of the world performed a different kind of thermal engineering on a monumental scale. In the highlands of South America, the Inca faced a challenge that was the mirror image of Roman luxury, not how to create warmth, but how to survive the killing cold of the Andean nights at altitudes where frost could destroy crops. Their solution was not a furnace under the floor, but a vast, invisible blanket of air drawn across the mountainside. The mystery lay in strange, patterned lines of stones that still scar the slopes above ancient terraces. For years, these were dismissed as agricultural clearings or ceremonial pathways, but when researchers began to map them with thermal cameras, a stunning pattern emerged on cold, clear nights. The stony areas, losing heat rapidly, became significantly colder than the surrounding soil. This temperature difference set the air in motion. Cold, dense air from the stony zones would begin to flow downhill like an invisible river, draining away from the precious terraces where crops like potatoes and maize were grown. This deliberate, engineered airflow prevented the frost from settling and forming the icy crystals that would destroy a harvest. Experimental projects went further, actually reconstructing these stone arrays and monitoring the microclimates they created. The data proved the effect was not accidental, but a predictable, repeatable result of the design. By simply rearranging stones already present in the landscape, Inca engineers harnessed the basic physics of convection, guiding the night air to protect their most vital resource. It was a form of climate control written not in machinery, but in the geology of the mountain itself, a silent, enduring technology that turned a hostile environment into a fertile one. This proven technique reveals a philosophy of profound integration, where the builder's role was not to impose a new system, but to gently redirect the existing forces of nature toward a sustaining purpose. The invisible highways of the ancient world were not paved with stone, but with ingenuity. Long before the first wheel turned on an axle, Neolithic communities across Europe faced a monumental puzzle: how to deliver colossal stones, some weighing many tons, across miles of rolling landscape to become the silent sentinels we call dolmens and menhirs. The sheer physicality of the task has fueled speculation for centuries, suggesting lost technologies or superhuman effort. Yet the answer, proven through repeated experiments from Cornwall to Karnak, is both elegantly simple and astonishingly effective. It is a system of 3 integrated parts: a wooden sledge to carry the stone, a series of round logs placed as rollers beneath it, and a prepared pathway lubricated with animal fat or a slick clay slurry. Experimental teams, using only these attested materials, have demonstrated that a coordinated group of 20 to 30 individuals, heaving on ropes and using wooden levers for guidance, can move a multi-ton block over remarkable distances with a steady, rhythmic efficiency. The physics is clear: the combination of the rollers and the lubricant reduces the coefficient of friction to a tiny fraction of what it would be dragging the stone directly over the ground. Each revolution of the logs converts sliding friction into the far easier rolling friction, while the greased track ensures the rollers themselves move smoothly, preventing them from digging into the earth and stalling the entire operation. The most compelling proof, however, lies not in the modern experiment but in the ancient ground itself. Archaeologists have discovered distinct, parallel grooves preserved in the subsoil at Neolithic sites, perfectly spaced to match the width of a sledge and the diameter of likely rollers. These are the fossilized ruts of a log rolling highway, the indelible signature left by a society that understood how to make the landscape itself cooperate with their vision. This proven technique transforms our image of these early builders from isolated mystics into masterful logisticians, capable of organizing labor, materials, and fundamental physics to orchestrate the slow, deliberate march of mountains across the land. While stone and earth provided enduring strength, the defense of an empire could rest on the command of a more terrifying element: fire. High on the walls of Constantinople, Byzantine engineers perfected a weapon so potent it became the stuff of legend: a liquid flame that burned even on water and could not be extinguished. The secret formula for this Greek fire is famously lost, a closely guarded state mystery, yet its true power was not solely in the chemistry, but in the machine that delivered it. Historical texts describe a crucial device, a bronze tube or siphon mounted on the decks of warships. For generations, this was just a description in a manuscript. Then experimental archaeologists decided to build it. Using the precise metallurgical techniques of the era, they cast a bronze pump with a sealed reservoir and a narrow nozzle. The test was not with the legendary formula, but with a thick, flammable substitute of similar viscosity. The results were devastatingly effective. By operating twin hand pumps, a crew could pressurize the reservoir and then release a valve. What emerged was not a weak trickle, but a roaring, continuous stream of liquid fire that could arch over the water for a startling distance. This proven delivery system transformed the weapon from a defensive hazard into an offensive terror. A ship could now aim and project fire with direction and range, even while maneuvering in battle. The pressurized siphon turned a flammable substance into a controlled, projected force. This experiment confirms a profound insight. The Byzantines mastered not just a terrifying substance, but the sophisticated mechanical engineering required to weaponize it. They built an ancient flamethrower, a fusion of chemistry and machinery that held their enemies at bay for centuries, proving that in the ancient world, technological supremacy could be the difference between a city's survival and its fall. A wall without mortar seems like a contradiction, a puzzle of stone destined to collapse. Yet across the rolling hills of the Scottish Highlands, you will find countless miles of these very structures, standing silent and immovable for centuries. These are not the ruins of a forgotten craft, but the enduring proof of one. Traditional dry stone walling is a language written in granite and limestone, and its grammar has been decoded through the patient work of modern wallers rebuilding by the ancient rules. The technique begins not with construction, but with a careful conversation with the landscape, selecting each stone for its specific role. The largest, most stable stones form the foundation, laid in a trench to prevent shifting. As the wall rises, every single stone is chosen and placed with intention, its longest face running across the width of the wall, locking the two sides together into a single, interwoven mass. This is the critical secret, the through stones. They act like stitches in fabric, binding the structure from within. The faces of the wall are then built with a subtle, inward lean, a batter that directs the tremendous weight of the stone downward and inward toward the wall's own heart, creating a stable wedge shape. The final masterstroke is what is left out, the mortar. In an experimental rebuild, you can witness the brilliance of this omission. Rainwater does not pool or freeze against a sealed surface. It simply percolates down through the countless tiny gaps, draining freely away from the core. The wall breathes when the ground freezes and heaves, or when a sheep leans against it. The entire structure can flex and settle as a unified whole, adjusting without cracking. A mortared wall in the same conditions would shatter. This proven method is a deep, empirical science of gravity, friction, and hydrology, learned over generations and tested by time itself. It transforms the scattered debris of a field into a legacy of order, a testament to the idea that true strength often lies not in rigid binding, but in intelligent arrangement, allowing the natural world to move as it must, while the hand-built form endures. Wood can be taught to dance with an earthquake. While the Japanese mastered resilient joints, their Chinese contemporaries developed a different kind of wooden genius, one that focused not on the frame itself, but on the critical junction where the roof meets its support. This is the realm of the DuGong bracket, an architectural marvel that looks more like a complex wooden puzzle than a structural component. To the untrained eye, it is a beautiful, layered cluster of interlocking blocks and bow-shaped arms, often ornately carved, sitting atop a stone column. For centuries, its purpose was assumed to be primarily decorative, a way to create the distinctive, sweeping eaves of Chinese temples. Experimental archaeology, however, has proven its true function to be one of life-saving engineering. Researchers built full-scale replicas of traditional DuGong frames and placed them on powerful shake tables, machines that simulate the violent, side-to-side lurching of a major tremor. The results were nothing short of revelatory. As the simulated ground shook, the DuGong bracket did not remain rigid. Instead, it performed a controlled, elastic dance. The multiple layers of wooden pieces, fitted together without nails or glue, began to slide and rock against one another. Friction between the wooden surfaces converted the destructive kinetic energy of the earthquake into harmless heat, dissipating it gradually through the entire, intricate lattice. The bow-shaped arms flexed and straightened, acting like springs to absorb the shock. This entire system acted as a sophisticated shock absorber, isolating the heavy, rigid roof from the columns below. By the time any force reached the main structural pillars, its destructive power had been dramatically reduced. This proven behavior is a form of ancient base isolation, a principle modern engineers use in skyscrapers today. It allowed pagodas like the Yingxian wooden pagoda, the oldest and tallest of its kind in the world, to stand for nearly 1,000 years in a seismically active region, surviving dozens of recorded quakes that leveled simpler structures around it. The DuGong bracket showcases a profound, intuitive understanding of dynamics, where beauty and resilience are not separate ideas, but are carved from the same piece of wood. It proves that safety was not found in immobility, but in a carefully calculated, graceful flexibility. White plaster was the skin of a Maya city, a luminous membrane that transformed pyramids and palaces into gleaming monuments against the jungle's green. But this was no simple coating. It was the product of a controlled industrial fire, a pyrotechnic ritual on a staggering scale. To produce the vast quantities needed, the Maya did not merely burn limestone, they orchestrated its transformation. The evidence for their method lay scattered around ancient cities, in the form of peculiar, slag-filled pits and mounds of partially burnt stone. Experimental archaeologists saw these not as waste but as blueprints. They began by digging a replica pit kiln, then carefully layered it with alternating strata of fist-sized limestone chunks and precisely measured firewood. The ignition was a critical moment. Once lit, the kiln had to be managed with intense focus, as teams used long poles to stir the burning mass, ensuring oxygen reached the core to sustain a ferocious heat. The goal was not just a fire, but a sustained thermal event. Sensors placed inside the experimental kilns recorded the crucial threshold. The temperature had to climb and hold above 900 degrees Celsius for many hours. At this sustained, searing heat, a chemical metamorphosis occurred. The limestone, which is calcium carbonate, shed its carbon dioxide, leaving behind a volatile, powdery substance known as quicklime or calcium oxide. This material was dangerously reactive. In the next proven step, workers would carefully add water to the quicklime, a process called slaking. This triggered a violent exothermic reaction, releasing clouds of steam and heat as the quicklime transformed into a smooth, workable lime putty. This putty was then the magic binder, mixed with local sand, clay, and sometimes crushed volcanic ash to create the final plaster. When applied in layers and burnished, it cured into a surface of legendary hardness, a shield against the tropical rains that could last for centuries. This entire chain of production, from layered kiln to gleaming wall, has been proven step by step. It reveals a society with a masterful command of chemistry and logistics. They understood that beauty and permanence were forged in the heart of a meticulously maintained fire, turning the very bedrock of their world into a radiant, protective skin for their civilization's grandest dreams. Deep within the arid landscapes of Western India, the earth itself opens into a realm of cool, geometric shadow. These are the stepwells or valves, monumental structures that descend like inverted temples, their symmetrical staircases marching down to meet the hidden water below. For centuries, their stunning beauty was apparent, but their full genius remained a quiet secret of the stone. It took modern researchers, armed with sensors and a desire to understand, to to prove that these were not merely ornate reservoirs, but sophisticated climate machines. By meticulously mapping their geometry and modeling their physics, a profound dual function was revealed. The most obvious purpose, the cascading steps, provided reliable access to a water table that could rise and fall dramatically with the seasons, ensuring a community could always reach this vital resource. But the true innovation lay in the Stepwell's hidden body, its vast subterranean chamber. Experimental models demonstrated how this sunken space leveraged the principle of evaporative cooling. As water slowly evaporated from the large, shaded surface area of the steps and central pool, it drew heat from the surrounding air. The dense, cool air would then settle in the depths of the well, creating a stable, refreshing microclimate that could be 20 degrees cooler than the scorching surface world above. Further tests on water flow and exposure proved another layer of intelligence. The step design, largely shielded from direct sun and wind, drastically reduced surface area evaporation compared to an open pond, passively conserving every precious drop. This proven technique transforms our view of the structure from a static container into a dynamic, responsive system. It was architecture in dialogue with the elements, using stone, geometry, and the simple physics of water and air to solve two critical problems at once: water security and thermal comfort. The Stepwell stands as a testament to a civilization that viewed scarcity not as a limit, but as a catalyst for monumental, beautiful ingenuity, crafting oases of coolness and community from the very challenge of the dry earth. The mastery of metal represents one of humanity's great technological leaps, and in the heart of ancient Africa, this process was refined into a quiet art of fire and chemistry. The Nok culture of what is now Nigeria left behind not only their famous terracotta sculptures, but also the subtle, clay-lined footprints of a profound industrial knowledge. For many years, Western scholarship often framed such achievements as imports from other regions, a narrative of diffusion that overlooked local genius. Experimental archaeology has now rewritten that story, proving the sophistication of indigenous African iron smelting through hands-on reconstruction. The process begins with the furnace itself, a cylindrical tower built from local clay. Researchers, following archaeological evidence, carefully formed these structures, incorporating the critical feature of clay pipes known as tires. These pipes were the arteries of the operation, channeling air directly into the heart of the fire. The true test came with the fuel and the breath of the furnace. Teams layered the chamber with a precise mix of crushed iron ore and charcoal, then put the bellows to work. Using reconstructed goat skin bellows, operators pumped a steady, forced draft through the tires. This was not merely blowing on a fire, it was a carefully managed chemical environment. The forced air raised the temperature inside the clay chamber to a specific, intense range, while also creating what is known as a reducing atmosphere, a chemical condition that strips oxygen from the iron ore. After hours of sustained, rhythmic work, the moment of truth arrived. Breaking open the cooled furnace revealed a spongy, glowing mass of metal mixed with slag, known as a bloom. This was raw, usable iron, produced entirely with locally sourced materials and a tested technology. This successful experiment proves several profound points. It demonstrates the efficiency of the forced draft system, a deliberate innovation that allowed for greater control and higher yields than a simple open fire. More importantly, it confirms the smelter's deep, empirical understanding of a complex chemical process, an understanding gained through generations of observation and refinement. This iron did not arrive from elsewhere, it was born from the earth, the trees, and the skilled hands of the community. It fueled tools, art, and society, standing as a powerful, proven testament to an independent technological tradition that flourished long before external contact, a legacy of innovation forged in the heart of a clay furnace. The final lesson in our journey is perhaps the most profound, for it is not about building a monument that stands still, but about constructing a vessel that can find a single, invisible point in an endless ocean. This is the proven mastery of Polynesian voyaging, a complete system of technology and knowledge that represents humanity's most audacious act of exploration. The double-hulled canoe, or wakolua, was itself a marvel of construction, its hulls painstakingly shaped and lashed together with thousands of feet of hand-braided cordage, its sails woven from resilient pandanus leaves. Modern reconstructions like the Hokulea proved this vessel's seaworthiness beyond doubt, but the true test was not of the boat alone, but of the mind guiding it. The navigator, or PWO, stepped aboard with no compass, no sextant, no map. Their instruments were the living world itself. They had memorized a celestial map, knowing which specific stars rose and set over each distant island. They learned to feel the subtle, deep ocean swells refracted by unseen land masses hundreds of miles away, reading the sea's texture like braille. They watched for the specific flight patterns of homing birds at dusk and the telltale reflection of lagoons on cloud bottoms. This entire body of knowledge, passed down through chance and apprenticeship, was put to the ultimate test on voyages that retraced ancient migratory routes across thousands of miles of open Pacific. When the Hokulea sailed from Hawaii to Tahiti using only these methods and arrived precisely at its target, it did more than complete a journey, it validated a science. This holistic technique proves a staggering truth. The settlement of the vast Pacific was no series of happy accidents. It was a deliberate, repeatable act of genius, a triumph of a living library built into the design of the canoe, the patterns of the stars, and the cultivated memory of the navigator. It stands as the ultimate example of experimental archaeology, where the entire ocean became the laboratory, and success was measured by the sight of a long-awaited shore rising from the horizon. This was not just construction, it was the building of a bridge across the greatest wilderness on Earth, using nothing but keen observation, profound environmental literacy, and the courage to trust in a knowledge as deep and old as the sea itself. The 20 proven techniques we have explored form more than a list. They are a constellation of intelligence. Each one, from the self-healing Roman concrete to the celestial maps of Polynesian navigators, reveals a universal truth about our ancestors. They were not primitive laborers stumbling upon solutions by accident. They were empirical scientists in the truest sense. Their laboratory was the world itself. Their experiments were the structures they built, and their data was recorded in the enduring success of what they left behind. This hands-on, iterative process of trial, observation, and refinement is the very heart of engineering. They understood the tensile strength of a bent sapling, the thermal mass of packed earth, and the fluid dynamics of a harbor not from abstract equations, but from a deep, tactile conversation with their materials. Their genius was contextual, born from a specific need within a specific environment, making their solutions models of breathtaking efficiency and sustainability. What experimental archaeology ultimately restores to these cultures is their full agency and intellect. For too long, monumental achievements were shrouded in a mist of mystery, sometimes attributed to outside influences or even mythical intervention. The rigorous proof of these methods sweeps that mist away. It shows us communities and individuals solving staggering problems with the resources and knowledge available to them. The Inca did not have the wheel, so they made stone flow. The Egyptians did not have steel, so they used sand to cut granite. The Polynesians did not have magnetic compasses, so they memorized the stars and waves. In every case, a perceived limitation became the catalyst for an ingenious, adaptive leap. This proven legacy fundamentally challenges how we view history. It asks us to see past peoples not as curiosities from a simpler time, but as our intellectual peers, They faced different constraints, but their capacity for observation, innovation, and collaborative problem-solving was equal to our own. This recovered knowledge is a forgotten textbook, its pages written in stone joints, mortar chemistry, and timber frames, and its lessons are urgently relevant. In an age grappling with the environmental costs of modern construction, these ancient techniques whisper alternatives. They speak of building with local, renewable materials, of designing structures that work with natural forces rather than constantly fighting them, and of creating legacies meant to endure for centuries, not just decades. The Maya plaster that defied the jungle, the earth lodge that breathed with the plains, the stepwell that created coolness from aridity, all point toward a philosophy of deep integration. This is not about abandoning modern technology, but about enriching it with a legacy of proven, sustainable ingenuity. The silent stones have spoken, and their message is clear: human creativity, when grounded in careful observation and respect for the world, can achieve the extraordinary. The final proof lies not just in what was built, but in the enduring invitation those structures extend, to look upon the past not as a mystery, but as a mentor. From the wet sand of Egypt to the star paths of Polynesia, our journey reveals a profound tapestry of human intelligence woven across millennia. Each experiment, each reconstructed tool, has pulled back the curtain on a past that was dynamic, inventive, and profoundly connected to the material world. These were not people stumbling in the dark, but keen observers and brilliant problem solvers, whose greatest technologies were born from a deep, respectful dialogue with their environment. They saw the desert not as an obstacle, but as a prepared highway. They understood that the sea could be a partner in building, and that the wind could be guided to protect a harvest. This is the recovered legacy of our ancestors, a legacy written not in fragile parchment, but in enduring stone, resilient wood, and self-healing concrete. These are not lost secrets, but rediscovered truths about our shared, fundamental capacity for innovation. They remind us that genius is not defined by the complexity of your tools, but by the clarity of your observation and the creativity of your application. As we face our own global challenges of sustainability and resilience, perhaps the greatest lesson is to look back at these time-tested solutions. They were born of patience, of careful observation, and of a philosophy that sought harmony with nature rather than domination over it. The silent stones have spoken, offering a forgotten textbook of ingenuity. Let this exploration be a starting point for your own curiosity. We would love to hear which of these 20 proven techniques amazed you the most. Share your thoughts in the comments below, and if you are eager to delve deeper into the mysteries history has left for us to solve, one experiment at a time, be sure to subscribe. Our journey through the echoes of the past is just beginning.